Hi everyone, welcome to this video on Group 1 metals. I'm also going to go through Group 7 and Group 0 just really quickly about their properties and things like that. So let's start with the alkali metals, Group 1. Okay, so this is things like lithium, sodium, potassium, rubidium, cesium and francium. So Group 1 means the column going down. It's on the periodic table, it would look like this, and then you just have a 1 above it, so that's Group 1. Okay, so because these elements are in Group 1, that means they have 1 electron in their outermost shell. So that's a really good way of knowing how many electrons are in the outermost shell. Just look at what group number that element is in. So 1 electron in the outermost shell. So these alkali metals are reactive and their reactivity increases down the group. So reactivity increases down the group. And this is because the outer electron is more easily lost as the attraction between the nucleus and the electron decreases. So let me just give you an example. Lithium will be a small atom like that, whereas francium will have a lot more shells and its outermost electron will be further away from the attraction of the nucleus. Therefore, because it's more further away, it's more easily lost because this attraction is weaker. This positive nucleus is attracted to the negative electron more strongly because it's closer, whereas here, because the outer electron is further away from the attraction of the positive nucleus, it can be more easily lost. So electron more easily lost. Let's just squeeze it on here, further away from the positive nucleus. Okay, so it's really important that you know that reasoning. So it's the outer electron is more easily lost as the attraction between the nucleus and the electron decreases because the atom gets larger and the electron is further away. Okay, let's just carry on with some more properties then. So they have low melting and low boiling points. So this is all Group 1 metals, low melting and low boiling points. They form ionic compounds. So ionic compounds, if you're not sure on what ions are or what ionic bonding is, I would go back and have a look at the video that I've made on ionic bonding. Okay, so ionic compounds with a 1+ charge. So remember, lithium, for example, has 3 electrons. It's more easy for this lithium atom to lose this 1 electron as opposed to gain 7 in order to make a full outer shell. It's easier to lose the 1. If we're losing electrons, if we're losing negativity, the charge becomes more positive. So I would end up with La+. If I'm losing electrons, if I'm losing negativity, the charge becomes positive. Okay, so alkali metals also react vigorously with water to form hydroxides. And these hydroxides dissolve in water to form alkaline solutions. So now you can see why we call them the alkali metals. So these hydroxides, and hydroxides have the ending OH, they dissolve in water to form alkaline solutions. So alkali meaning if I had some universal indicator in that water, it would go from green to purple because it's an alkali solution. So let me give you an example. It's really important you know these word and symbol equations for all these elements. So I'll just show you generally what happens then. So let's take sodium. Sodium plus water, so I'm reacting with water, and I form a hydroxide, a metal hydroxide, sodium hydroxide. So I'm taking the metal at the start, and because I'm reacting with water, I end with hydroxide, and then I also get hydrogen gas forming. So this is not a balanced equation. In order to balance it, you just put 2's in front of those 3 compounds and elements there. So I'll just repeat that this is sodium hydroxide, and it's the same with any of the alkali metals. Let's try lithium. Lithium plus water goes to lithium hydroxide plus hydrogen. So that's the general pattern. Hydroxide forms plus hydrogen. Okay? Next equation you need to know then is the reaction of alkali metals with chlorine. So the reaction with chlorine and alkali metals produces a salt, what we call a salt. So sodium plus chlorine goes to sodium chloride, and that's my salt. Sodium chloride salt. So it's not sodium chlorine because it's a salt and we've used chlorine there. Oh, sorry, I've made a mistake there. That should be Cl2 because chlorine exists as a diatomic molecule. It's not sodium chlorine, it's always sodium chloride when we're talking about the salt. Okay, next one is the reaction with oxygen. So do make sure you're making a note of all these word equations. This is generally how you work them out. Okay, alkali metals with oxygen, we form metal oxides. So again, lithium plus oxygen goes to lithium oxide. Sodium plus oxygen goes to sodium oxide. With potassium, it's a little bit different. Potassium plus oxygen, we form potassium dioxide here because we've got 2 oxygens. So just be aware of that one, having a little bit of a difference there. Okay, so that's your group 1 alkali metals for you. Let's move on to group 7, the halogens. Okay, so group 7, known as the halogens. Okay, so we are looking at fluorine, chlorine, bromine, iodine and astatine. So they always exist as diatomic molecules. When they're on their own, they always exist in pairs. So it's F2, Cl2, Br2, I2, At with a little 2. So you need to know what they look like, what these elements look like at room temperature. So here's a few things to memorize. Fluorine is always a yellow gas. Chlorine is a green gas. So this is at room temperature. Bromine is a red-brown liquid. Iodine is a dark grey solid, or a purple vapour. You'd get a mark for whichever one you put, that's fine. Don't need to know about astatine, they don't tend to usually ask you about that one. Okay, so going down the group, they get less reactive as you go down the group. So less reactive as you go down the group. So fluorine, therefore, is the most reactive. And this is because it's harder to gain 1 electron when the shell is further away from the nucleus. So for example, fluorine, because it's in group 7, it will have 7 electrons in its outer shell. It can easily attract another electron because the positive nucleus can draw that electron in quite easily. Whereas if I'm looking at iodine, which has more shells, and the 7 electrons, oh sorry, I've drawn that really bad, and the 7 electrons in the outermost shell, need one more, it's going to be harder for this extra electron to join on because you've got a bigger distance, you've got a bigger atomic radii or bigger distance between the positively charged nucleus and the negatively charged electron. And that's why reactivity decreases down the group. Okay, so they have high melting and boiling points. They form covalent bonds. So covalent bonds mean the sharing of electron pairs. So for example, HCl. So Cl is my halogen. They form covalent bonds with non-metals. So chlorine is in group 7. So it has 7 electrons. I'm only going to draw the outermost electrons. 7. Hydrogen has 1 electron. So now if you have a look, hydrogen, because we're sharing an electron pair, one from chlorine, one from hydrogen, hydrogen has now got 2 in its outermost shell. Chlorine has 1, 2, 3, 4, 5, 6, 7, 8. They've both got a full outer shell of 8 electrons and therefore they're stable. So that's how halogens covalently bond. They can also form ionic bonds with metals. So form ionic bonds with metals. So ionic bonding is the giving and receiving of electrons. So for example, let's try NaCl. So Na has 1 electron in its outermost shell, Cl has 7. What can happen is the sodium can give an electron to chlorine, which needs 8, in order to form Na plus, because we've lost an electron, lost negativity, and Cl minus, because we've gained an electron. And this electrostatic attraction between the positively charged ion and the negatively charged ion is what forms the compound NaCl. That's ionic bonding, this electrostatic attraction, which basically means positive and negatives attract, which we know from magnets and things like that, which is what forms ionic bonding. Okay, last little bit on halogens then, displacement. So displacement means to remove and replace. So more reactive halogens will displace the less reactive halogen in a salt. So I'll just write that for you. More reactive halogens will displace, remove and replace the less reactive halogen in a salt. So let me give you an example. Chlorine plus potassium iodide goes to iodine plus potassium chloride. So just notice my pronunciation here. Chlorine, INE, because it's just an element on its own, a diatomic molecule. This is potassium iodide, so IDE. When the halogen is attached to another element, it turns into the halide and it ends with IDE. So iodine here, an element on its own, INE, potassium chloride. So when it's a salt, it turns into the halide and you end with IDE, potassium chloride. Okay, that's really, really important to remember and be able to do that in an exam. Okay, so chlorine is above, I'll quickly just draw it on the side. So this is group 7. So group 7, we go from fluorine, chlorine, bromine, iodine, astatine. So this is going down the group, okay? Right, so chlorine is above iodine on the periodic table in group 7. Therefore, chlorine is more reactive than iodine. So chlorine can displace, can kick out, can remove and replace iodine from the salt. That's why iodine ends up on its own like that, and chlorine attaches to potassium and forms a salt. Okay, let me give you one other example. Let's do fluorine plus K Br goes to Br2 plus Kf. Right then, so we've got fluorine, INE, potassium bromide goes to bromine, and potassium fluoride. So fluorine is above bromine on the periodic table, therefore it's more reactive, it's stronger. So it can come in, kick out bromine, and leave bromine on its own and form the salt potassium fluoride. Again, when these halogens exist on their own, they exist as diatomic molecules. When they're attached, they're just as one. Okay, so not always will you get a more reactive halogen. So for example, iodine plus potassium bromide. Iodine is weaker than bromine. Therefore, iodine cannot replace bromine. It's always the halogen. Is it stronger than the halide in the salt? Okay, so it's not the other way around. We're not asking, is bromine more reactive than iodine? That it's this way round. Okay, the halogen on its own, can that kick out the halide in the salt? No. Therefore, we'd get no reaction. So you can either write no reaction or you can write the same reactants, equal products, like that. Okay, that's group 7 done then, that's the halogens done. Let's quickly move on to group 8 or group 0. Group 0 or group 8. And these are called the noble gases. Right, so we are looking at helium, neon, argon, krypton, xenon, and radon, I think. Oh God, what's RN? Let me just quickly check. Oh yes, it's radon. Okay, so radon, along with all the other noble gases, have a full outer shell. They have 8 electrons in the outermost shell. Therefore, they're stable. They don't need to lose or gain electrons like the others because they're already stable. They've got their full outer shell. So they're unreactive. They exist as monatomic gases. Monatomic meaning one. So for instance, I was just talking about the halogens existing as diatomic molecules, so F2, whereas here with the noble gases, they just exist as one. You would never ever see helium as a pair or anything else. It's always just on its own as it is with the other noble gases. So they don't bond, they're just singular. Okay, so they're all colourless gases at room temperature. And they're all non-flammable. Okay, so that's their properties then. Their boiling point, so boiling point and melting point, increases down the group. So increases as you go down the group. And this is because, sorry, I can't speak. This is because as the atom gets larger, there are more electrons present in the shells. You get more shells, therefore more electrons. And the intermolecular forces need to be overcome, and they're overcome using energy, and that's why boiling point and melting point increase. So let me give you an example. Helium has 2 electrons, whereas as we get all the way down to xenon, it will have its lots more electrons, its full outer shell. I'll just mention actually, so here, group 0 or group 8, I've said before, the group number tells you how many electrons are in the outermost shell. So helium is the exception here. Helium only has 2 electrons, so it doesn't have 8 in its outermost shell, but it has a stable full outer first shell, only one shell, with 2 electrons. So just be aware of that. Helium still has a full outer shell, but it's just the first shell because it's only got 2 electrons, and that's it. We can't go any further. But all the rest do have 8 electrons in its outermost shell. So as the atom gets larger, you get more electrons. So all in here, you know, you'd get all your electrons, loads more, like this. So more electrons, meaning greater intermolecular forces. Greater intermolecular forces. And you need more energy. I'll just squeeze it on here. More energy needed to overcome these forces. And in this case, boiling and melting point, we're talking about heat energy. Okay, I hope you enjoyed that video. Quick summary on group 7, group 1 and group 8. Okay, see you in the next video. Bye.